Hi, I'm Zor. Welcome to Zor Education. I will talk about operations on vectors, certain fundamental operations. It's basically vector arithmetic. Now, when we talk about arithmetic, we usually have in mind numbers and manipulation with numbers like addition, subtraction, multiplication, and division. That's basic arithmetic. Now, with vectors, we will be dealing under the topic arithmetic, addition and subtraction of vectors. And as far as multiplication and division, we will be considering multiplication by a real number and division by a real number, not multiplication vector by vector. This is a separate topic. There are two kinds of multiplication of vector by vector. One is called scalar or dot product, and another is called vector or cross product, and that will be separate topics. So today this lecture is about multiplication and division by real numbers and addition and subtraction of vectors. Now, vectors are new objects. Mathematicians just came up with this. It's something which combines in itself the length and the direction, these two components. Now, the operations, arithmetic operations on vectors should be defined, how should I say it, naturally. So people who deal with these operations would agree that this is exactly what operations of addition or subtraction or multiplication by 25 are supposed to be. So this natural approach is very important. So any kind of a definition should be justified by some common sense. And that's what I will try to explain in this lecture. I will try to put some common sense behind the definition of arithmetic operation. Okay, so let's start. The first operation which I wanted to define is multiplication of the vector by a natural number, like multiplication by 2, multiplication by 25, multiplication by 1, for instance. Now, how naturally can it be defined? Well, what I'm suggesting right now, and that's what actually mathematicians decided to define, is very simple thing. If you have a vector, then to multiply it by 2, 1, 25, or whatever else is retain the direction of the vector and just make it longer by this factor, by 2, by 25, by 1, whatever it is. Well, by the way, in particular, multiplication by 1 means that the length will stay exactly the same. So since we retain the direction, so the vector stays the same, which basically implies the rule that multiplication by 1 doesn't change the vector. Multiplication by 2 makes it twice as long, so it will be about that long. Multiplication by 25 would be 25 times longer. I consider this a very natural definition. Now, what's also very important is that certain properties of multiplication which we used to have with numbers, for instance, commutative law, associative law, will definitely be preserved here. I don't want to prove it right now. I will probably do it as a problem, actually, which means I will ask you to prove it first, and then I will explain in the lecture. But yes, all these laws are supposed to be held. So for instance, if you have a vector, I will use the lowercase letter and arrow on the top, and you multiply it by number m, and then the result, now this is m times longer than a originally was, and the result I'm multiplying by n, so it will be even n times more than that. What does it actually mean? It's the vector which has exactly the same direction as a, but its length will be multiplied by m and then multiplied by n. But length is a real number, which means whether we multiply it by m and then n, or by n and then m, in any order. So these are supposed to be exactly the same results. So this is some very, very brief introduction to proof of all these laws. But I don't want to stop any longer. I will introduce a little later this. So this is multiplication by a natural number. It's easy. It's natural. And that's why it's natural. All right. Now, how about division? Well, division by a natural number, let's just think again. What is the definition of the division if you're dealing with numbers? What does it mean that 6 divided by 3 is equal to 2? Well, it actually means that 2 multiplied by 3 is 6, right? So, in case of vectors, if I want to divide vector by n, it actually means to find another vector which, if multiplied by n, would give a. Now, obviously, if you take exactly the same direction and just shorten the lengths by the factor of n, so this would be 1/n of the original vector, then obviously if multiplied by n, using whatever the definition I just talked about, how to multiply vector by some natural number, I will get the original a. So that's why dividing by natural number n is very simple. You just retain the direction and shorten the lengths of the vector by this particular factor. Now, if we can multiply by a natural number and we can divide by a natural number, and all these manipulations are with lengths only, which is the real number, obviously what we can do now, we can multiply vector by any rational number, because it actually means first you multiply it by m, and we know how to do it, and then you divide it by n, and we know how to do that. And again, since all these manipulations are with lengths only, direction is the same as before, then these are just manipulations with real numbers, and we know that we can multiply by a rational number by first multiplying by numerator and then dividing by denominator. So we cover the rational numbers, positive rational numbers, mind you. All right. How about irrational numbers? Well, irrational number can always be represented as a limit case of rational numbers. We did talk about this. So for any irrational number, there is always a sequence of rational which is approaching it infinitely closely. So basically we can introduce the same type of approach. I don't want to do it very rigorously right now, but in theory, if you know how to multiply by rational numbers, approximation of any irrational, like square root of 2 for instance, with rational numbers would give you basically the definition of the multiplication of the vector by irrational number as a limit case of multiplication by rational numbers. Okay. Now, and by the way, all these manipulations, multiplication by rational, irrational, positive numbers, obviously would conform to commutative and associative laws. Again, I don't want to rigorously prove it right now. I will leave it for later, for the problems. But it should be really felt by anybody, since we are only manipulating with the lengths, and length is just a real number. Then all the laws which are applicable to multiplication of the real numbers are applicable here. Okay. Next, I would like to spend some time. Now, by the way, I did not cover negative numbers, only positive. Okay. Now, well, I have this sequence of introduction which would introduce negative numbers a little later, and I do have some reasons for this. So let's just follow this particular structure. So next, what I would like to do is I would like to define how to add two vectors which are directed identically, just have different lengths. Well, again, since these two are identically directed, then we can always bring them to common beginning, let's say beginning of coordinates, this will be one vector, and this would be another vector. Now, they are actually coinciding, so don't pay attention that it's kind of two separate lines. One lies on the top of another. Now, what can be the sum of these? Well, let's just think about what's the physical meaning, for instance, of a vector. Well, it can be a force. So we have some object, and one force, pressure by my hand, for instance, can be expressed in some kind of a vector, and then something else would pull it, let's say, with another force towards the same direction. Now, what would be the sum of these forces? Well, you just basically say this is sum. So you have to sum the lengths of one vector and lengths of another vector, and again retain the same direction. So manipulation of these vectors, the addition of these vectors, which have identical direction, should result in the vector which has identical direction with these two, and the lengths, the magnitude of this vector, should be equal to the real sum of these two lengths. I think it's very natural. Obviously, it conforms to all these commutative and associative laws of addition, because again, you don't really change direction. All vectors, two operands, and the result, the sum of these two, are all identically directed. So all we manipulate is the lengths. We add one length to another to get the result. And obviously, it works like the addition of real numbers, basically. So this is a definition of addition of identically directed vectors. Okay, so I'm introducing these operations just step by step, trying to make simple ones first, and then I will complicate the issue. Next, what I would like to talk about is something which I would call a null vector. Now, null vector, as the name implies, has the length null. But in this case, it's very difficult to talk about direction, right? Null vector can graphically be represented as a dot, basically. So there is no way you can put this arrow. So this vector has certain length, so you can put some arrow at the end, and that's the direction. Point does not have a direction. So when I'm talking about null vector, I can actually say that this null vector has either no direction, or you can consider it directed to anywhere you want. It doesn't really matter. Now, what's interesting about this? Well, let's add this vector and this vector, the real vector and the null vector. Well, since null vector can take any direction I want, but it has a length 0, well, why don't I say that, okay, in this particular case, if I would like to add it to this particular vector, it has the same direction. And in which case, the result would be the vector of the same direction, and the lengths equal to sum of two lengths, right? Now, this is 0, the length is 0. So if I will sum them up, I will get exactly the same lengths. So the result of addition of a null vector to any vector would be exactly the same vector we are adding it to. So this particular concept, null vector, and operation of addition is really working exactly like with numbers. You can add 0 to any number and the number will not change. Okay, so that's the concept of a null vector. Now, what's next? Next is multiplication by 0. So we knew how to multiply by positive numbers, rational, not non-rational, irrational. Now, how about multiplication by 0? Well, I can always say that the multiplication by 0 gives me null vector. So this 0 is a number, the multiplier. This 0 with this little arrow on the top signifies a null vector. So multiplication of any vector by factor 0 will result in null vector. Now, it actually completely corresponds to the idea of a null vector and the multiplication. The length is always multiplied, right? So the direction is retained when I'm multiplying, and the length is multiplied by the factor. Factor is 0, so the result of this multiplication is vector which has the length of 0. And I don't really care about direction because this is a 0, this is the null vector. So I can say that null vector has exactly the same direction as I. There is nothing wrong. There is nothing wrong with that. All right. So we know how to multiply vector by 0. The result is null vector. Okay. What else? Now I would like to say the following. I would like to expand my definition of addition from identically directed vectors to opposite directed vector. Let's think about again what is vectors meaning from the physical sense or mechanical, whatever. Well, mechanically, for instance, it might signify a displacement, movement. This means I moved from this point to this, and this means I moved from this point to this. Well, obviously, the result of summation of these two should be I just did not move at all. I was standing still. Similarly with forces. If you have two forces directed against each other and they're both applied to the same object, they nullify each other and the object stands still, basically, doesn't move anywhere. So it's very natural to define the operation of addition of these two vectors which have exactly the same lengths and they are directed opposite to each other. It makes sense to define their sum as null vector because they kind of nullify each other, right? So if I would add a vector with another vector which has opposite direction but the same lengths, I will get 0. So that's what basically it means. All right, that's good. Now let's consider a little bit more complicated case. What if this is not the same lengths? And I would like to add them together. Well, let's not forget that we would like our laws, which we are defining right now, to be nice, natural, commutative, associative, etc. So what actually might happen in this particular case is the following. I can always represent this vector as a sum of vector which is directed the same direction as this one, but the length should be equal to this one, and then another piece. So it's like a sum of these two vectors. This one plus this one. Now, if I will sum them together, now, obviously, again, I'm assuming that whatever we are defining must be associative and commutative, etc. So we kind of think about this as these two pieces should nullify each other, and only this one would remain, right? Now, how to describe all this process in a little bit more mathematical form? Well, very simply. So if you have two vectors which are directed in opposite direction, first of all, you determine the result of their sum. The result would be the same as the one which has a greater length, which is this in this particular case. Now, what would be the length of the result? Well, you just have to subtract from this length, subtract this one, and then you will get this piece. And that's the result of summation of two vectors which are directed opposite to each other. By the way, from the position of just defining certain new concepts, there is a concept which is called collinear vectors. These are vectors which are basically along the parallel lines always, which means either they are identically directed or opposite to each other, but it's still within the same direction. So vectors which have direction either identical or opposite to each other, they're lying like on the same line, or lines are parallel depending on where exactly these vectors are positioned in space. So they're called collinear, which means they're sharing the same line along which they're both stretching, either in the same direction or opposite. All right, so we have completely defined the operation on collinear vectors, right? Now, next is, I would like to return back to multiplication. Now, we have completely defined quite well, actually, everything about positive factors, which we multiply the vector. Now, how about negative? Well, first of all, I would like to define multiplication by -1. Now, multiplication by -1, I will define as collinear vector, but directed opposite to the one to the A, the one which I'm starting from. Well, it's exactly the same as with numbers. If you have 5, you multiply 5 by -1, you get -5. So -5 and 5 are symmetrical. They have the same distance from 0. So they're very much similar to two vectors which are directed opposite to each other, but they are collinear. So if I will get this as a definition, then from this I can obviously define multiplication by any negative number, k, where k is less than 0, as multiplication by -1, and then multiplication by absolute value of k, right? So since k is negative, multiplication by -1 and absolute value of k should give me exactly the same thing, because -1 times absolute value of k would actually give me the k if k is less than 0, right? So I know, again, using the associativity, commutative law, etc., I can always say that, okay, I know how to do this. This is just a vector which is directed opposite to the A, and then I know how to multiply by a positive constant, positive real number. It's already defined before. So now this actually completes the multiplication case. So I can multiply by any constant, positive, negative, 0, rational, whatever. All right, what's left? Left is the most interesting part. This is something which usually many teachers just introduce from the very beginning. Okay, this is a definition of the addition of two vectors. And then they basically present what I'm going to present right now. I did all the explanation before this just to gradually bring you to this particular concept. So now we are talking about two vectors which are not collinear. They do not necessarily have the same lengths, but let's consider they are of different direction and different lengths. And the question is how to define naturally, properly, nicely, if you wish. You can attach even some other epithets, but anyway, how to define the sum of these two vectors. Again, let's go back to physical interpretation of the vector. Let's consider vector represents a displacement. So whenever I'm moving from one point to another, that displacement is characterized by this vector, direction and the length I moved. And this is another move. Now, what does it mean that I would like to add together two moves? Let's say I move 1 mile north and then 1 mile west. Well, first you move 1 mile north, right? Then you take this vector attach it at the end. So from here, I put it in such a way that the origin of this vector coincides with the endpoint of the first operand. So this is A, this is B, this is also B. It has exactly the same length and exactly the same direction, but I positioned it at the end of the first movement. So what's the result of my movement? Well, that's the displacement, which is this. Right? So the rule to add together two vectors which are not necessarily collinear and not necessarily the same lengths is you take one vector, now at the very end you attach another vector which is exactly the same directed and the lengths the same as the second operand, and the end point of that together with the original point of the first vector of the A would give me the lengths and direction of the combined movement. So that's the definition. Now, does this definition is more or less the same in case vectors are collinear? Well, yes, because for instance, B and A are collinear, and I will just put the B as a continuation of A. Obviously, their lengths will add together, and it completely corresponds to my original definition of the addition of two collinear, identically directed vectors. How about opposite direction? Well, it's exactly the same thing, because if this is A, this is B, what's the result? From the beginning of A to the end of B, which is this particular piece. And that's exactly what I was talking about when I was saying that from the bigger lengths you should subtract the smaller one, and the result would be the same, the direction would be the same as the bigger vector. Okay. Now, how else this can be represented? Well, it can slightly differently be drawn, if you wish. Because notice that this is parallelogram. Why? Because this is equal to that. Vectors are equal, it means they are equal in length and parallel. And that's why it's parallelogram. There is actually a theorem about quadrilateral with opposite sides parallel and equal to each other, that this is parallelogram. And the result of summation is basically a diagonal. So another way to present exactly the same way is not to move B to the end of A, but instead build a parallelogram on these two which are originated at the same point. So you build the parallelogram and take its diagonal from the same point. This is a rule of parallelogram which is in physics actually very much used in many different places. That's how we add forces together. So if you have, for instance, two forces acting on the same object at different magnitudes and different directions, what's the resulting force? Well, that's the rule of parallelogram, because that's exactly how vectors are added together. So we found how to add two vectors. Okay. What's left? Subtraction, right? How to subtract two vectors. Well, but let's think about it. What does it mean? Well, it means basically this. Right? So, if I want to subtract from A, I want to subtract B. I would like to find out the vector which is, if added to B, would give me A. Now, so basically, obviously, this is the vector. So it starts from the endpoint of the B and ends at the endpoint of A. And indeed, if I will add B and C, I will get A. Right? Because that's how I define the addition. So subtraction is very easy, as I said. Now, what's interesting, and this is just again some kind of side note, we would like to have certain arithmetic rules which we used to have to be true for vectors as well. Remember, 5 minus 3 is equal to 2. 5 plus minus 3 is equal to 2. 5 plus minus 1 times 3 is equal to 2, right? Now, how about vectors? Well, let's think about what if I will do, instead of that, I will do this. Would it be exactly the same? Well, let's just think about this geometrically. Now, this is A, this is B. Now, what's B multiplied by minus 1? It's this one. It's minus 1 times B. Now, this is C, which is equal to A minus B. Now, how about A plus this vector? Well, let's just put this parallel shift to this. This is also be minus 1 times B. So if I add A and minus 1 times B, I will get this. It's very easy to prove, and I will probably prove it in some problem, but it's very easy to prove that these two are exactly the same. They have the same lengths and the same direction. So this is just an illustration to solution which will be in some other lecture, which will follow this particular one. So I was just trying to give you a taste of certain problems which I would probably ask you to solve, and then I will present the solutions myself. All these problems about these arithmetic operations on vectors, to prove that they actually exactly conform to operations with numbers. And one more thing. You remember that vectors have not only geometric representation, but also a tuple representation as an ordered set of numbers. And in particular, set of two numbers represent the vector on the plane. Set of three numbers, a tuple of three tuple, as it's called, represent the vector in three-dimensional space. Now, so the question now is how these representations, tuple representations, are changing with arithmetic operations. But this also will be part of the problems which we will be solving together. Because after I have defined, I mean, this lecture is just an introduction to arithmetic operation. That's where I define these operations, and how these operations affect certain different representation of the vector is a different story, and it will be addressed in subsequent lecture. So far, that's it for today. Thank you very much. I encourage you to go through notes for this lecture on unizor.com. That's in the part which is dedicated to vectors, and I think the topic is called exactly like this: arithmetic, vector arithmetic. I think that's how it's called. Yeah, that's how I call this lecture, vector arithmetic. So that's it for today. Thank you very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to present you a couple of problems related to vector arithmetics, like addition, multiplication by constant, etc. Now these problems are quite trivial, but I would like to use this opportunity to basically tell about certain standard symbolics which are used in the vector arithmetic. So what I will be using for vectors are usually lowercase Latin letters with arrow or just a bar on the top, depending on. And if this is a vector, then in its tuple representation, I will try to use the same letters as coordinates with indices. Like this is a three-dimensional tuple representation of vector v. Now, another thing is lengths of the vector. Now, the lengths, I will use double bars. That's the lengths. By the way, sometimes the lengths is called a norm of the vector. Now, this is the term which is borrowed from a little bit more abstract concept of vector spaces. So norm or length, just exactly the same, so I will use it. And obviously in this particular case I can always say that this is a three-dimensional length, or norm of the vector v, expressed as an algebraic expression of its tuple representation. In this case, it's three-dimensional coordinate system. All right, so that's all about different symbols which are used. Now let's just do the problems. Okay, the first problem. Let's consider a vector v with tuple representation v1, v2. Let's say it's two-dimensional. Actually, for three-dimensional, it would be exactly the same. Now, let's consider the vector which is the result of multiplication of this particular vector v by some real number k. Now, what happens with coordinates? Well, the theorem states that coordinates are also multiplied. So, multiplication of the vector by a constant results in the tuple representation, multiplication by this constant every component of the tuple representation. So every coordinate of the vector. Now, let's just consider this as a geometric problem. Okay, this is my coordinate system. And this is my vector. So these are v1 and v2 coordinates of this vector. Now, if I multiply by, well, let's say in this case a positive constant first, what happens? Well, direction is the same of the result of the multiplication by the constant, but the length is increasing by that particular number. So let's say k is something like 2, for instance. Doesn't really matter. So this line goes twice as long. Now, what are the coordinates of this next vector? So if this is b, this is kv. So from 0 to a is v, and from 0 to b is k times v. Now, it's quite obvious that triangles A1, A2, B1, B2. Triangles OA, A1 and OB, B1 are similar, obviously, right? Because we know that the triangles are right triangles, right? Because this is right angle. Now, this angle is retained, it's common, it's shared, because when we multiply the vector by some number, we retain direction. Direction is an angle, so the angle is exactly the same, which means another angle is also the same. So two right triangles with the same angles, they're obviously similar, which means that everything is proportional. Now, since the proportion of the hypotenuses is k, it's exactly the same proportion of catetus. OA1 relates to OAB1 as OA to OB. So this is exactly the same. Same thing with catetus AA1 relative to BB1. So the same coefficient of proportionality exists for the length of the vector itself, which is hypotenuse, and on each catetus, which are coordinates of the tuple representation. So that's why it's true. Now, for a negative k, situation is absolutely the same, because all it does is just reverse the picture towards the other direction. So if this is k, this would be multiplication. I mean, if this is v vector, then this would be multiplication by negative. And since direction is changed on the opposite, these angles are still the same, which means that again the triangles are similar and the proportionality between the lengths of the hypotenuses would be exactly the same as the coefficient of proportionality between the catetuses. And obviously, if this is positive, then this is negative, and that would be that would signify that the same sign of k is the coefficient of proportionality between the category of this and category of these triangles. So positive or negative k, everything is exactly the same. It's all similarity of triangles. Now, what happens? Okay, so we have actually found that the multiplication of the vector by a constant is basically reflected in the tuple representation as multiplication of each component by this particular constant. That's done. Now, how about the lengths of the vector? So if you will take the lengths of this vector, which is the result of multiplication of the vector v by k, that's the new vector, and what's its lengths? Well, we know that the lengths of the vector multiplied by a constant is supposed to be obviously longer by that particular constant, right? Now, the only thing I cannot really write this way because k might be negative. So this is a true length, right? So this is always the positive thing. So we cannot just have plain k. We have to play absolute value of k. So absolute value of k times norm of the vector v is the norm of the vector kv. So that's the second problem. So multiplication by a vector by any real number results in the lengths being multiplied by absolute value of that particular real number. That's the number 2 problem. Okay, now what happens with coordinates of the vectors when we add them up? Let's say you have two vectors, v and w, in tuple representation. And again, I'm using two-dimensional case because it's easier to draw. Basically, it's the same for any dimensional. So, what happens with tuple representation of the sum of these two vectors? Okay, let's just write the answer. Now, the tuple representation of the sum of two vectors is sum of the corresponding coordinates. Now, well, this is for three-dimensional case. Now we have two-dimensional case. Right? All right. How can we make sure that this is true? Well, let's just go again geometrically. So let's say we have vector v, and this is vector w. Now, when we want to add them up, you remember the rule. We take the vector w, and we attach it at the end of the vector v by parallel shift, forming the parallelogram, right? So if this is A, this is B, this is C, so AC vector is exactly the same as OB, and this is W. All right? Now, let's think about coordinates. This coordinate, A1, this is B1, and this is C1. Now, obviously, since we took this OB and parallel shifted to AC, then the coordinate of the OC would be greater than coordinate of A by the coordinate of the OB, right? So the coordinate of OB, the x-coordinate in this particular case, is OB1. So what I'm saying is that OC1 is equal to OA1 plus AB. OC1 is equal to OA1 plus A1C1. Right? But A1C1, this one, it's projection of this particular vector, HC, onto the x-axis, which is exactly the same as projection of OB, right? So that's equal to plus OB1. This is the same vector as this one. So projection of this vector onto the x-axis, which is A1C1, is exactly the same as projection of this vector on the same axis, which is OB1. And this is obviously OA1 is projection of the vector OA on the x-axis, which is V1, and OB1 is W1, projection of the OB of the vector W on the x-axis. So OC1, this is an x-coordinate of the sum of these two vectors, right? I didn't draw the sum, but this is the sum, right? OC as a vector is equal to OA as a vector plus OB as a vector. So that's what it is with x-coordinate. Now, projection onto y-axis is exactly the same logic, everything is the same. So that's why the projection on the y-axis of the sum of two vectors would be sum of its projections. So when you sum two vectors in their tuple representation, you just add the corresponding coordinates. But by the way, the first problem was when you multiply vector by a constant, you multiply corresponding components of the tuple representation. Now when you add two vectors, you correspondingly add coordinates in the tuple representation. So it's a very, very natural and very easy to remember rule, basically, right? All right. How about difference? Okay. I'm sure you expect this, which is absolutely correct. Now, I can probably prove it in many different ways, but let's say for a second, if V minus W equals U, what does it mean? It means V is equal to U plus W. So U has to have coordinates U1, U2. This is W1, W2. And V is V1, V2. So right? So u1 plus w1 should be v1, which means u1 should be v1 minus w1. Now, u2 plus w2 should be equal to v2. Therefore, v2 minus w2 is equal to u2. So that's one of the ways to do it, purely algebraically. Another way is just to draw a picture, and you will see basically that's exactly the same rule as we used for addition would be applicable to subtraction of two vectors. Without going into many details, if you have these two vectors, this is v and this is w, then v minus w is this one, right? This is u equal v minus w. Now, w plus u gives you v, right? That's right. Now, and if you compare the coordinates of these points, the projections of these vectors on the x-axis, for instance, then obviously, if this is a and this is b, this is b1 and this is a1, then obviously, if you subtract from OB, you subtract OA1, you will get A1, B1, which is projection of this vector onto the x-axis, which is first x coordinate in the tuple representation. And same thing with y coordinates. So either or, algebraically or geometrically, we can prove it. Okay. Now, from these two previous problems, I would like to prove this subtracting a vector is exactly the same as adding the vector which is opposite in direction and the same as length, which is multiplication by minus 1. Addition of this particular opposite vector. So it's like with numbers, right? 5 minus 3 is exactly the same as 5 plus minus 1 times 3, right? Which is minus 3. Now, with vectors, it's very simply actually to show, well, one of the easiest way, for instance, is, okay, let's consider coordinate representation, tuple representation. Now, what do we have in this case? Well, the representation of this is b1, v2, this is w1, w2, and the difference we already know by previous problem is v1 minus w1 and v2 minus w2. Now, what about this? This is v1, v2 plus minus 1 times w1, w2. Now, this is, as we know, multiplication by a constant results in the multiplication of each component in the tuple representation. So it's exactly the same as minus w1, w2. Now, when you add these two things in the tuple representation, coordinates are added together. So v1 is added to w1. And v2, w2. Same thing. Well, as you see, we have exactly the same result, which proves that subtracting a vector is exactly the same as adding that vector multiplied by minus 1, or if you wish, adding an opposite vector. Okay. The last problem is this one. The length of the sum of two vectors is less than or equal to lengths of the one plus let's just consider this from the geometric perspective. We don't even need coordinates, quite frankly. Because if this is the v vector, now this is a w vector. This is a v plus w vector. What does it say? That the length of the sum is less than sum of these two lengths, which is a triangle inequality. It's inequality which is known for all the triangles. So geometrically, this is basically obvious. It results from the triangle inequality which we learned before in the corresponding chapter related to geometry. But let's think about, can we do it algebraically? Not because it's better, but it might be really interesting to approach it not from the geometric perspective, but from the algebraic perspective, tuple representation and expression of the lengths in terms of tuple components. Actually, we can do it. It's a little bit longer, but I think it has certain value just because you will familiarize yourself with manipulation with tuple representation. So let's say these are tuple representation, and I'm talking about two-dimensional case. That's easy. Now, the tuple representation of v plus w is v1 plus w1, v2 plus w2. Now, how is norm or a length of the vector with coordinates x1, x2 expressed algebraically? Well, you know it's this one. That's Pythagorean theorem, and we spoke about this in the corresponding lecture about lengths of the vectors. So, what's this length? Well, it's square root of first component square, which is v1 plus w1 square, and v2 plus second component square. That's on the left. That's what we have to prove. And this one, right, that's the length of this vector in tuple representation, less than or equal to length of the first one plus length of the second one. Right? That's what we have to prove. Now, well, let's see if we can do it, right? If we can do it algebraically, where all numbers, v1, v2, w1, w2, are just real numbers, right? So this is a pure algebra. Prove this particular inequality. Well, let's see if we can do it. First of all, everything is positive here. So if we will prove instead of this, if we will prove the square of this, it will be the same, right? It's equivalent. So we're talking about lengths, so everything is positive here. This is positive, and this is arithmetic value of the square root. All right, so let's square both sides. This square would be everything without the radical, obviously, and I will open up the parentheses. It will be v1 squared plus 2v1 w1 plus w1 squared plus v2 squared, 2v2 w2 plus w2 squared. Right? That's on the left. And we have to prove that this is less than or equal to square of this, which is square of the first one, plus 2 square root of their product, v1 square plus v2 square, w1 square plus w2 square, plus square root square of this second component. That's what you have to prove. obviously we can reduce by this, right? Everything goes out. And I will also reduce by 2. Because here 2, and this is 2, and this is 2. So what's remaining is V1 W1 plus V2 W2. That's on the left, should be less than or equal to square root of, well, let me multiply them. V1 square W1 square plus V2 square W1 square plus V1 W2 square plus V2 square W2 square. That's what I have to prove. Again, let's just think about everything positive. I don't want to worry about the negative signs. Let's consider everything is positive. It's just easier to do it this way. So consider we are only dealing with vectors in the first quadrant, because everything else would be exactly similar. It's just easier for me to go without thinking about not exactly being backward compatible. But in this case, if everything is positive, then I don't have any problem with it. So let's square it again, both sides. So on the left I will have V1 squared W1 squared plus 2W plus 2 V1 V2 W1 W2 plus V2 squared W2 squared less than or equal to this. I will not change anything. Okay, now we have to reduce something, I guess. This one and this one. And this one and this one. So, what remains? This, and this. And I will transfer this to the right by subtracting from both sides 2 V1, V2, W1, W2. And what I have is V2 W1 square plus V1 W2 square minus 2 V1 V2 W1 W2, and it should be greater than equal to 0, right? I just wrote it from right to left. So this is on the right, and this used to be on the left, but I put it also on the right, but with a minus sign. Now, what is this? Is this right? No. V1 W1 minus V1 W2 square. Square of this, which is this, minus 2 product, which is this, and square of this, which is this. And this is an obvious inequality, because this is a square, so it's greater than or equal to 0. Now, so from something which I had to prove by squaring a couple of times and reducing whatever is necessary, I came to an obvious thing. Now, is everything is reversible? Well, almost, because as I said, in a couple of cases, I said, okay, let's just not think about negative sides. I probably should go much more rigorously if I would really want to prove it in all the general cases. I can start with this and then gradually go backwards and reduce whatever the different cases of negative coordinates or something else. I probably could have done it a little bit, more rigorously. But in any case, what I would like you to see in this particular case, that I have used a purely algebraic approach to something which seems to be like a geometric problem, lengths of the vectors. In any case, it doesn't really matter that it's much longer. It's not for achieving the results. The purpose of this is not really to prove. I can prove it geometrically much simpler using the triangle inequality. But then again, how did I prove the triangle inequality? I mean, that's also a separate theme. So that's why it's always interesting to approach the problem from different sides to get the same result. So this is a mental exercise rather than like, something which you have to remember or anything like that. But if you think about this, everything I'm talking about here is basically your mental exercise, just to make your brain functioning, and it doesn't matter how you use it, what you use it, it's all the same. It's all to train your brain to think creatively. Well, that's it. That's it for today. These, whatever 6 problems are very, very easy. They're basically based on definitions of whatever the concepts we were talking about. But why don't you just go through these problems again, just by yourself? They are presented on the website unizor.com. If you will go to vectors part and the topic is vector arithmetic, that's the problems where that's where these problems are presented to you. So thanks very much and good luck. Hi, I'm Zor. Welcome to Unizor Education. Continuing the topic of vector arithmetics. In the previous lecture, I was talking about how the addition of the vectors and multiplication of the vectors by a constant can be expressed in a tuple form. So let me just repeat very briefly. If, let's say, we have a vector which has a tuple representation, well, this is a three-dimensional vector. Actually, it's exactly the same with two-dimensionals, etc. Then multiplication by this vector by a constant can be expressed in the tuple representation as multiplication by each coordinate by the same constant. That's one thing which we were discussing in the previous lecture. And the second one about addition, if you have another vector in tuple representation, then addition of these two vectors has a tuple representation when you have add corresponding coordinates to obtain the coordinates of the result. Now, these two fundamental properties of multiplication of the vector by a constant and addition of two vectors are very important in proving certain properties of the multiplication and addition. Now, the properties which we know from the numbers are commutative law, associative law, distributive law. Remember that commutative law is this one. When A and B are any numbers, the associative law is about additions and about multiplication. So in addition case, it's this one. You can put the parentheses any way you would like. So first you add A and B and then add C to the result, or you add B and C and add this to result of this to A. Same thing with multiplication. You can multiply it this way, or you can multiply it this way. And finally, there is a distributive law, which is to multiply the number by a sum of two other numbers is the same as multiplication of this number by the first, separately by the second, and then add them together. So these very nice properties of the multiplication and addition of the numbers can be very easily extended towards vectors, because what is a vector? It's just in a tuple representation an ordered set of 2, 3, or maybe even more numbers depending on the dimensionality of the vector. So if something is true for one number, why can't it be true for a group of 2 or 3 numbers, right? And yes, indeed this is true. So this lecture is about all these laws of associative law, commutative law, and distributive law as we know them. We will expand them towards the vectors using the tuple representation. So the group of numbers behaves exactly the same as single numbers, basically. That's what we would like to show. Okay, so I presented this particular lecture in the form of problems, actually, and I'm really asking you to do all these problems yourself, because they're very, very easy. If you use the tuple representation to prove all these properties, it's really a piece of cake. So I'll do it as fast as I can, because it's really a very, very simple thing. First, would like to prove that constant multiplied by vector can be commutative. Well, very easy. Let's think about this. This is k multiplied by vector. Let's say v is v1, v2. I'm using two-dimensional case. Three-dimensional would be exactly the same as, and actually n-dimensional would be exactly the same. So k times v is equal to k v1, k v2. Right? Multiplication by vector is multiplication of these. Now, what is multiplication of constant by vector we were talking about? What is multiplication of vector by the constant? Well, it's actually from the definition of this follows that these are exactly the same. Why? Because if you remember multiplication by a constant, let's talk about constant equal to a natural number, like 4. What does it mean? You preserve the direction and you increase the length by 4 times, right? So multiplication of constant by vector should be defined actually exactly the same as multiplication of the vector by the constant, because it has this physical sense. Multiplication means you will just extend the length of the vector 4 times, or whatever number of times, preserving the direction. If k is negative, you remember we were just changing the direction by opposite, and it should be defined exactly the same thing. So we can actually say that this is the result of the definition of the vector, its physical sense. And then, obviously, from the tuple representation, it's exactly the same, because vk would be defined as v1k, v2k. And since numbers, multiplication of numbers is commutative, kv1 is the same as v1k, kv2 is the same as v2k, because these are just real numbers. Each one of them is a separate real number. So real numbers are commutative as far as the multiplication is concerned. So that's why the commutative law of the multiplication of the vector by a real constant is obvious. Next we will go to associative law, but this is not just the regular associative law. This is a combination of the multiplication of vector by 2 constants. So we can do it this way, right? Or we can do it this way. So first we multiply two numbers by themselves and then the result by a vector. Or we multiply one number by a vector and then the result is a new vector which is multiplied by another number. Now, why are they equal to each other? For exactly the same reason. So again, if V is V1, V2, then what is this? This is K, L, V1, K, L, V2. That's what it is. So the tuple representation of this is this constant, K times L, multiplied by the first coordinate and by the second coordinate. Now, what is this? Well, these are two different multiplications. First, L times V would be L times V would be L V1, L V2, right? Now, whenever we multiply K by this vector would be K times L times V1, K times L times V2. Now, is this the same as this? Yes, absolutely, because the multiplication is associative, same as here. I should really put these parentheses to be more precise, right? Because we first multiply by L. But now KL times V1 is the same as K times L times V1, because multiplication of the real numbers is associative, and each one of them is a real number. So as you see, the group of numbers behaves exactly the same as single number as far as the associativity is concerned, or commutative law. And obviously we have defined all these operations on vectors exactly having in mind that these laws must be preserved. That's why it was designed this way. All right, so associative multiplication of the vector by two numbers is proven. Next, addition of two vectors is commutative. So V times W equals W times plus V. Okay. Same thing, very obvious from the representation. If V is V1, V2, and W is W1, W2, then V plus W is V1 plus W1, V2 plus W2. Now, what is W plus V? Well, this is W1 plus V1, W2 plus V2. But these are equal to each other, right? Because the commutative law of addition of real numbers. So if these two tuple representations are the same, so vectors are the same, that's the proof of it. As you see, everything is very simple as soon as we switch to a tuple representation, because the corresponding law of, in this particular case, for instance, commutative law of addition between vectors is reduced to the commutative law of addition of the real numbers, which represent each corresponding dimension. In this case, like two-dimensional, can be three-dimensional, any number of dimensions. Okay, next is associative law. Let's say we have of addition. So let's say we have three vectors. So first we add these two, and in this case we add these two. So this is associative law of addition. Now, why are they equal? All right, well, first let's just add these two. Now, this sum in tuple representation would be U1 plus V1, U2 plus V2. That's tuple representation of this vector. plus w, which is this one. Results will be u1 plus v1 plus w1, u2 plus v2 plus w2. That's this one. Okay, now let's talk about these guys. Now these guys are, first we summarize these two, which will result in v1 plus w1, v2 plus w2. And now we have to add to this vector, vector u. And u is, I didn't write it down, but u is u1, u2, right? So that would be, so we add u1, which is u1 plus v1 plus w1, and u2 plus v2 plus w2. As you see, we have exactly the same result, which proves the associative law of addition among vectors. Now let's talk about distributive law. Well, distributive law is when we mix together addition and multiplication, right? So in this particular case, we have a kind of a mix case, because when we multiply, we multiply vector by a constant. So the question is, what are we distributing? We're distributing addition of vectors multiplied by a constant, which is that's the distribution of addition towards multiplication. Or we distribute addition of the constant. So what are we talking about? Well, the answer is both. All right? So let's talk about the first one. Now, v plus w in a tuple representation would be v1 plus w1, v2 plus w2 in a two-dimensional case. And when we multiply it by k, what do we have? Well, we multiply each constant, each coordinate by this constant, right? So it would be k times this and k times this. Now, this is multiplication of real numbers and addition of real numbers. So the distributive law works. So I can open up these parentheses and I will have this. That's the final result on the left. On the right, I will have first kv1, kv2. That's this vector. And I have to add kw1, kw2. And when we add vectors, their coordinates are adding together. So it would be kv1 plus kw1. And the second coordinate would be kv2 plus kw2, which is exactly the same as this one. So that's the proof of the first line. Now let's talk about the second line. Well, when we multiply sum, first you multiply this sum by the first component and then by the second component, right? Which we can open up the parentheses because these are all numbers, so it's k v1 plus l v1, k v2 plus l v2. That's our left side of this line. Now on the right side Well, let's multiply constant k by vector v1, and we will have kv1, kv2 in the tuple representation, and I have to add lv1 plus, no, not plus, second coordinate, lv2. And when we add these two vectors in tuple representation, their constants, their coordinates are correspondingly added together. So I will have this. That's the first coordinate, and this is the second coordinate. So that's my right side. And as you see, it's exactly the same as the left side. That concludes all these very, very simple properties of the vector arithmetic. So just don't forget that to add, to multiply whatever vectors is exactly as simply as you operate with numbers, as long as you're using the tuple representation of the vectors. So it's very easy to add vectors, you just add coordinates. It's very easy to multiply vectors, you just multiply the coordinates by whatever the constant is. We're talking about multiplication by the constant. And whatever the laws of addition and multiplication of real numbers exist in arithmetic, exactly the same laws exist in vector arithmetic. Well, that concludes this lecture. I do suggest you to exercise again these little theorems. They are all presented as notes to the lecture on unizor.com. And, well, make sure that you understand all these manipulations with vectors using the tuple representation, because that's actually the only representation people are dealing with when they are trying to approach things expressed as vectors analytically, because analytically means basically using the tuple representation, not the graphics. Graphics are good for some kind of illustration purposes. When you draw a vector and then you add another vector, and then this is the sum of two vectors. It's all nice pictures and it all explains quite well. But analytically you have to approach it using the tuple representation with coordinates. And that actually implies the dimensionality of the vectors, two-dimensional vector, three-dimensional vectors, n-dimensional vectors, whatever. All right, that's it for today. Thank you very much and good luck.